So in the last video, we looked at the deviance as a way to measure the goodness of fit of a Poisson regression model. And in this lesson, we'll look at an alternative to that. So an alternative to the deviance is Pearson's chi-squared test. And so generally, the Pearson's chi-squared test statistic will look like the following. So it will be a sum from I equals 1 up to n. So the general way that it's written is something like this. OI, where OI is the number of observations, so this would be the count, say, in a Poisson regression, or in a binomial regression it would be the number of successes in n trials, minus what you would expect under some assumed distribution, and we would square that and then divide by EI. So again here, OI is the number of observations, EI is the expected or the mean number of observations under some assumed distribution. So if we were to write that out specifically for Poisson regression, we would have YI stand in for our OI, right? YI is just the count, it's the thing that comes from the Poisson distribution. And then what we would expect under the assumption that our model fits correctly would just be our stand-in for the mean. So it would be the MLE of lambda I. And then we would divide by that term again, right? The estimated mean. And for Poisson regression, turns out that this, well, in any case, not just for Poisson regression, but generally this thing would have a chi-square distribution with n minus p plus 1 degrees of freedom. And this can also be thought of as a measure of goodness of fit. So we could use this statistic as an alternative to the deviance when trying to assess goodness of fit. And oftentimes these two measures, the chi-squared test and the deviance test, will be very similar. And the null hypothesis would be that the model fits well, and a large chi-squared test statistic would be evidence against the null that the model is sufficient. So notice that we can actually interpret the terms that we're summing over as a standardized residual. So in the numerator, this quantity here should look a lot like a squared residual, right? We're taking the thing that we actually measure, the yi, and we're subtracting off the estimated mean. So that's analogous to what we had as yi hat in normal linear regression. So that is a residual. And then this term that we're dividing by, you could interpret it as a variance. So this is the estimated variance. And the reason for that is because the Poisson distribution, the mean and the variance are the same. So you're subtracting off the mean in the top, and you're dividing by the mean, but that's also the variance. So this whole term is actually a squared residual, a standardized residual, because we're dividing by the standard deviation but then squaring it. So that whole thing is a squared standardized residual, and we're summing over them. And so in the last lesson we saw how to define the deviance residuals, and here we have the Pearson residuals, which maybe we would call PI for Pearson residuals, and they'll just be YI minus lambda I hat divided by the square root of lambda I hat. So again, those things will be standard normal, and we could look at, say, plots of those against the estimated linear predictor and check for for structure, for example.